And this is the presentation of group 4. What we have tried to do is just to neglect the parts that other groups have mentioned and just try to somehow stress out the results, which were somehow the highlights of our works. So first of all, we need to know what is a landslide. Landslide is a downward movement of masses like soil, rocks, or a combination of them together. Then we need to know what are the types of the landslides. We can have different types of landslides such as topples, falls, slides, or complex ones, which is like a combination of all of them together. And here is like a presentation, a schematic presentation of landslide. Here, this part is the crown part. This part is the top part, the head of the landslide, and the top part is called the zone of depletion. The bottom part is the zone of accumulation. This is the comparison between two experiments. We have tried to keep all the conditions similar and change only one condition in our experiment 1 to somehow investigate in the effects of that change, that condition. So as you can see here in the experiment 1, we had 3 layers of 5 centimeter, all of them compacted sand. So one uniform layer in terms of physical characteristics. In experiment 1, however, we have 2 layers of 7.5 centimeters. The top layer is uncompacted sand and the bottom layer is compacted one. And we have tried to investigate in the effect of how this variation in physical characteristics will change the results of our experiment. So this is the comparison between the TDR sensor results. As I said, the rainfall event is similar. The water pressure intensity of rainfall is similar. So we can see a very similar trend, like the slope is very the same. The differences, there are 2 differences in them. The first one is this highlight. The experiment 1, as we said, the top layer is uncompacted sand. So the water penetrates easily, more easily, like comparing with the experiment 0. And the other highlight is this part, like the blue one is experiment 0. As you can see here, it has somehow a very aggressive failure comparing with the experiment 1. Then we have the comparison between the tensiometer results. The highlight of this part is this volatility here, which is due to the ceramic heads not being fully filled with water. This is also somehow confirmed with this part. As you can see, the result of tensiometer 1 has gone more than 0. So it shows that the water goes inside the ceramic head from the soil. So it again confirms that the ceramic head was not filled with water. Another highlight, sorry. So this is the comparison between the Arduino sensor results. As I said, we use the same rainfall event in both experiments. Here is, we have the rainfall, then we measured the runoff, collected the runoff actually, and the differences of them give us the infiltration. I'm going to talk about this figure later. We have provided a table of anomalies in our experiment, like there are 7 anomalies explained in details in our report. Among those 7, I'm going to talk about the first one, which is the failure of experiment 1. It's the same anomaly as we have in number 6 and number 7, but in different, let's say, instruments. So this is anomaly number 4 here. In volumetric water content, you can see the decrease here. In tensiometer, again, we have at the same time, 15, 18, there is this sharp increase in the results of the tensiometer. And also it was seen in the Arduino sensor results, this one here, again, around the time 15, 18. So all of them corresponds to the same anomaly. We have investigated in the results of in this anomaly to see like what is the roots of this behavior, unexpected behavior. So looking at the photogrammetry, this is like the last failure, the collapse of our slope, as we said. And here the results of from the geophysics. Here we can see this is the model which had happened, which has been taken like after the time of that failure. As you can see here, there is this dark blue color which is corresponding to very large values of resistivity, which shows the presence of cracks and voids. Then we have somehow done a numerical modeling just to have a brief introduction over that, we have statistical models or the machine learning models which take into account only the rainfall events. They neglect the physical characteristics. We have physical models which are integrated with geographic information systems. They are computationally very expensive, so we cannot use them in a regional scale. But the model that we used was a sleep model. It's a combination of physical model and a numerical model. It's based on the limit equilibrium method. And in the sleep model, we have two layers. It is assumed that the bottom layer is assumed to be the collection of saturated zones. So we have one saturated layer here in the bottom, and we have the top layer which is partially saturated. The factor of safety is calculated from the differences of the stabilizing forces and destabilizing forces. Again, I'm going to dive deep into this later. This is the result of safety factor. As you can see here, it gives the time of the first crack almost 4 minutes before what happened in the experiment. Let's see why this happened. As I said, there are two limits in the sleep model. One of them is neglecting the runoff water. In sleep model, we assume all of the water infiltrates. And the other one is considering a uniform layer. So, but in our experiment, we have two different layers. The top layer was not compacted. We have tried to tackle these two limitations of the sleep model. And before explaining those, there are like the sensitivity analysis or the sleep model. This is sensitivity to the slope, which is very sensitive. This is the sensitivity of the sleep model to the friction angle, which again shows high sensitivity, and the sensitivity to the porosity, which is not very sensitive. Let's tackle those two limitations of the sleep model. The first one was neglecting the runoff water. We have done another sensitivity analysis for different percentages of rainfall being considered as the runoff water. So we have tried to assume 75% of the rainfall event infiltrates into the slope, and 25% of that goes out of the runoff water. And this assumption was also confirmed by comparing the values of runoff and rainfall in this graph. This is actually from the actual experiment. So 25% is a good, let's say, assumption. Another modification that we did into the sleep model, as we said, these are default parameters in the limit equilibrium equation. It somehow considers the whole slope as one single layer with single characteristics. We have tried to modify these values with these modifications, like assuming two layers by multiplying them by 0.5. And in the bottom layer, we have tried to use, somehow decrease the porosity because of the compaction by 15% and use this 0.85, let's say, number here multiplied to the porosity. By doing these modifications, the sleep model gave us accurately the time of first crack. And also, there are some suggestions for doing a better experiment. One of them is like the boundary condition problem. The rainfall, some amount of rainfall occurs, like hits this wall, the highlighted yellow wall here, and that one goes into these boundaries. So if we can somehow change the way of the rainfall and collect it, we can somehow remove this problem. And this was seen like actually in every single experiment. The failure started happening either on the left or on the right side. So this was due to the boundary condition problem. Another problem was in the collecting runoff water, which you can see here, like a lot of water is not measured. Another problem that we had was regarding the geophysical sensors. We placed them, all of them, like in a row here. So if our crack starts happening from this part, we miss the first initial parts of the first initial cracks. So what we suggest is like increasing the distance between the geophysical sensors twice and putting them in another row, like either on this side and this side. In that way, we can somehow get the initial cracks even because we have the geophysical sensors on both sides. My friend will continue with the photogrammetry part.
Thank you, Mehdi. My name is Ahmed Gamal. I'm going to talk about the photogrammetry. Before definition of photogrammetry, what's photogrammetry? Photogrammetry is the science of digital image of a service, so we can have more relationship on the service itself from spatial data or from point cloud. We used photogrammetry for two main purposes. The first is spatial data of the fractures to get its placement and the velocity of different cracks that happen. And the second one is to have point cloud of the landslide. And once we have the point cloud, which is in our case a dense point cloud, we can have different relationships like 3D image. We can have also distance difference that we can compute the volumetric change. The techniques that we have used in the photogrammetry are the three. The first is 2D digital image correlation. The second is structure for motion, and the third is the laser data, laser kind of data. Starting with the 2D digital image correlation, we have to define main parameter, which is the ground sampling distance, which is based on the focal length, distance from the object to the lens of the camera, and the pixel size. Our GSD for experiment 1 and 0 is 0.632 millimeter per pixel. Secondly, we have tried to, in the MATLAB, to decrease the computational cost of the MATLAB to better have a sense of the algorithm that's happening. So we have divided our mesh into two parts. The first is the mesh part, the mesh very fine mesh, and the part that there was a lot of cracks. And the other one is the coarse mesh, which is the part of the landslide that didn't have any cracks. By this, we try to optimize the computational cost. We have categorized our cracks to 14 different cracks based on the naked camera, the fighter camera, and we have obtained these graphs, which the first one shows the displacement, and the second one which shows the velocity, and I'm going to talk in details about each fracture. Talking in details about fracture 1 that happened at the two of the landslide, we can see from the graph the maximum displacement that happened. Here it's 0.7 millimeter, and the time of the fracture, which happened at 2 p.m. 75 minutes. We have done the same analysis for different fractures, 14 ones, to get the same kind of data. Also, we got the velocity result. From the velocity, we can understand the progression or the aggression of the crack. As you see here, the crack that happened at the very beginning, it was kind of a very small crack that was in a very weak part of the landslide due to the infiltrated water. However, comparing it with another crack which is characterized by a higher displacement, we can see the difference between the two behavior. We can see like the first crack is a bit less, let's say weak one, not major displacement, and the other one happened as a very big displacement and aggression in terms of velocity. Secondly, we have computed the 3D image of the displacement pixels. We can see here at crack number 4 the number of pixels that have been displaced, and near crack number 8 we can see like a lot more pixels that have been displaced. And from these images we could better understand what was happening in terms of the displacement of the crack. The outcome of the 2D digital image correlation is this graph. We have tried to categorize our fracture into 3 different phases. The first one is the minor fracture phase, which is about like, it has all the fractures that have very small displacement, very small velocity. And then we have the second phase, which has much more bigger fractures in terms of velocity and displacement. And the last one is the critical phase, when we have a very transitional sliding of the soil. So this is the outcome of the 2D digital image correlation. And since we have the timing of each fracture, and for example, fracture number 1 happened at 2 p.m. 75, fracture number 2 happened at 3 p.m. 15 minutes, so we know the time difference. And comparing or correlating this data with the geological and geophysical, we can correlate the volumetric water content. For example, for fracture 2, we know what was the value of the volumetric water content and what was the timing of the fracture itself. Correlating these two images or these two information, we can have something that we call early warning system. We know this fracture happened at this exact time when this volumetric water content present. So by this value, at the end of the presentation, I'm going to introduce something called early warning system using these two pieces of information. The last part of the 2D digital image correlation is experiment 0. We have the same analysis for experiment 0. And what we could get is these 2 points as a comparison of experiment 0 and experiment 1. Experiment 0 was kind of characterized by gradual increase followed by a sudden failure. As you see here, gradual increase and then sudden failure. and the other one was more of phase failure and progression failure. And also we can see that experiment 0 has a small time difference between each fracture. And this could be due to the homogeneity or the homogeneous soil that was present in experiment 0, because two layers, both of them are compacted. Experiment 1, it was not two layers of the same characteristics. One was compacted and the other was uncompacted. The last part that I'm going to talk about is the structure for motion. We try to have a 3D image. First of all, we have calibrated the camera using 48 targets on the ground, and we have tried to align the images that we have from the 3 flare cameras using the target that was on the fume test. After alignment, we have got the dense point cloud, then we got the mesh with not texture, and then we've added texture. And then we've done orthophotos, and the orthophotos can help us to have the actual displacement of the fracture because it's kind of scaled. However, the scale of the orthophotos was 2, doubled by 2. So we compared the displacement coming from the orthophotos with the displacement coming from the GIC. And we can see here the GIC gave us a displacement of fracture 7 equal 1.2 centimeter, and the orthophotos give us 1.35. So the error was kind of 20% between the orthophotos and the GIC. And we have explained this in our report that uncertainties could be due to the blurring and the lightening and the algorithm of the GIC. For the last part, which is the laser scanner, we wanted to have a dense cloud using the laser scanner scans and to compute the volumetric change. First, we had 3 scans. The first one was very good, the second was very good, the third was kind of distorted into the rainfall, so we only used 2 scans instead of 3. We were lucky in our experiment that our 2 scans were aligned, there was no any vertical shifting, so we just needed to geo-reference them using the 5 targets geo-referenced by its total station. Then we computed the normal vectors, which show the local orientation of each dense cloud, and then we computed the volume computation, and we can see here the volume change of the added volume is equal 26 cubic centimeter, and the removed volume is 21 centimeter. And this difference due to that there was some soil part that was in the buckets that were not calculated or not seen in the scans. From this image also we can identify very, very important aspects in the landslide, which is the main parts of the landslide. From these scans we can see the ground, we can see the main scarp, and then we can see the 2 of the landslide. And then as the last part for the laser scanner, we have computed the distance difference using 3 different methods. The first one is C2C, cloud to cloud, and the second cloud to mesh, and the third is multi-modal cloud compared. We can see the cloud is not assigned method, so it shows a good result, but not as accurate or precise as the cloud to mesh or the M332. So we can see here that the MC32 was the one in our case that showed the accurate result compared with the volume computation display. The last part in the photogrammetry and the last slide in my part, we have introduced early warning system. As I said, from the photogrammetry we can know the time of the fracture. From the geology we can know the volumetric water content. And also we can know the same parameter from the geophysics, the volumetric water content after calibration using our keyboard. So we have introduced some kind of instrument that can help us to know when the crash is going to happen. So we said like we can have a piezometer which can be placed at the 2 of the landslide. And with this piezometer read the value of 0.18 volumetric water content. That means there's going to be having a failure or a crack after 5 minutes of this value. Once the piezometer reads this value, there's going to be a crack after 5 minutes. And this is going to give us a lead time of 5 minutes. People can evacuate, the authorities can do their work. And also, this can give us extra 8 minutes, extra 4 minutes before the extra major cracks. So 5 minutes before major cracks and 9 minutes before extra critical cracks. That was my part, and now my colleagues are going to talk about geophysics.
Hi, my name is and now I'm going to finish the geophysical part about the landslide. We can know that in this part we use the DC resistivity method, and the resistivity measurement is using the ERT with the linear array. We put the electrocodes every 3 centimeters with the cables connecting to the instruments. And then we do the resistivity model pictures of T2, T3, and T4. During these three pictures, we can find that the whole slope resistivity of the soil is decreasing. It's because of the rainfall stars, the water saturation becomes increasing. And we can find, especially during the toy of the slope, there is very low resistivity. We can assume that it's because of gravity of the water, so they may concentrate it on the toy part. And we can also find that this decreasing in soil resistivity wasn't in a smooth trend. This maybe have two reasons. The first reason is that the infiltration of this water is not so uniform. And second reason maybe is also because the sprinkler produce the rainfall not in a uniform way. And then we go the later part about T5, T6, and because the PowerPoint is not enough space to put all the points. So I put T10 as a representation of the time. We can see from this T5 and T6 that the soil resistivity began to increase in the chrome part. Meanwhile, the toy part keeps decreasing. In that case, we thought that still because of the water gravity, they are more concentrated in the downslope, so that the chrome part is increasing, but the resistivity is smaller than 200 O, so we cannot consider it as a real crack, but only a room of different water saturation. But we can know from the photogrammetry that especially our crack happens on T4, from T4. But our electricals don't record this data. Our guess is that because in our experiment, the crack happens in a very toy part of the slope, but our electricals are located in the center of the slope. In that case, so the electricals maybe don't record the resistivity where until the T10, we can see here, there has a very blue part that has a really large resistivity. Until now, the electrons finally realized that we have a big crack here, a big collapse here. And then we go to the mathematical resistivity model. You may use the Archie-law to build the mathematical resistivity model. If the resistivity is equal to the formation resistivity factor, multiply the water saturation, multiply the water resistivity. In that case, how we do it? First, we assume A and N, and to get the mathematical resistivity, and we compare the inverted resistivity comes from the software. In order to get a better, let's say, to get their similar, and finally we get a proto A and N here. But in our experiment, we can find the relative difference is quite high. We considering why about this problem. There is my answer about this. First thing is that because our soil we think is not compacted very uniform, and the second thing is because of that. Also, the thing I referred before is that our crack happens very toy, so in the toy part, so our electricals don't record data where. That's also caused quite difference here, comparison here. And the third reason is that during the experiment, we are different people are responsible for different parts. So when we do the time measuring, they are not in the same time, so maybe not so accurate. And finally, as a result, we develop a equation here. It's a water saturation of the landslide body from the inverted resistivity data. And we produce a graph here. We can see that the resistivity is always decreasing while the water saturation increasing, but it's not a very linear way. First, it decreases very rapidly, and here there is, and about the 40%, the resistivity decreasing becomes soft and gently, and finally we're getting close to zero. And the resistivity model experiment 0 is the same process as we explained before about experiment 1, but the main point we need to mention here is that during experiment 0, the cracks happens here. We can see, as we know, the electricals are located here. So in that case, electricals record the data really where. We can see from here, the T6, the resistivity is really large here. This part is also corresponding to the photogrammetry part. To conclude is that our three parts results from geology, photogrammetry, and geophysics are the supplementaries to each other. And finished. Let's go on with it.
are Shabnam.
Shabnam.
Can I start? During our field trip assessment, our area of interest was the Lano, which is a small town in the province of Lecco. And we considered these three main families for our discontinuities. The instrument that have been used in our field trip was the Schmidt hammer for measuring the hardness, Barton combs for measuring the roughness, geological compass with the help of plano application for measuring the orientation of the joints. Roughness characterization, which gives us this parameter that we analyzed and measured before. The last but not least is aperture. Aperture is a perpendicular distance between rock walls of a discontinuity. This is our measurement, and based on this classification of separation of joints is very tight. Joint family, as we're processing the data in a StereoNet, we can see that this is family number 1, family number 2, and family number 3, and this is mean vector of each family. A kinematic analysis, as you can see in that figure, we have concentration of pools, therefore there is no circular failure. For planar failure, we need to consider 4 conditions. The first one is the dip of slope must be greater than the dip of discontinuity. And the dip of discontinuity must be greater than friction angle. And also, the discontinuity daylights the slope face, and also it should be within plus and minus 20 degrees. Based on these 4 conditions, we don't have planar failure either. For wedge failure and toppling, as you can see, for wedge failure, we need to consider 3 conditions as well. The dip of intersection line must be lower than the dip of slope. And also, the dip of intersection line must be greater than friction angle. And also, the intersection line must daylight the slope face. Therefore, we don't have wedge failure either. For toppling, we need to consider 2 conditions. First, the dip of discontinuity must be more than 70 degrees. It means that it should be quite vertical. So there is no, it is not true for this condition. As for the first time, for the first one, the slope should be the same as the plane, but totally on the opposite side. Therefore, there is no toppling as well. For blood volume estimation, based on this formula, we obtained it for average, minimum, and maximum. And because of that, our resistance was not 100%, we need to use this formula instead. Based on this blood volume estimation for average, minimum, and maximum, we calculate safety distance evaluation based on the formula above, and also additionally we have calculated the X distance for 3 values that you can see in the last. I will allow you to continue.
Our purpose in photogrammetry is to generate 3D models of the rock surface, and at the same time to obtain the detailed direction of the families. The results give us a chance to do a comparison between software and in-situ results. By comparing these results, we can understand our errors and we can identify our mistakes. In the first, we took a picture in our field area to create them in our MetaShape. When we uploaded our photos on the MetaShape, we have to follow some specific steps in orderly. The targets are detected by automatically on MetaShape. However, we have to also do this detection manually to not use any of them. And then that is the alignment of the targets. After photos are targets, bars are scaled by optimizing cameras. With that way we decrease the error. The most important part of using MetaShape is to to produce the point cloud, because we use this point cloud on the cloud compared to find the deep direction values. Another most important thing, our point cloud should be oriented with respect to north. However, we didn't have geo-reference data. For this reason, we created our coordinate by itself. We had horizontal and vertical bars. Based on our coordinates, we started our target from 0, 0, 0 point, and then based on the difference between the targets, we revised the coordinates. After this optimization, we created our point cloud, dense point cloud, mesh model, and the texture of the surface as a 3D model. And then we transfer our data to the cloud compared to find the deep and deep direction. These points were organized in cells based on the KD tree. The main purpose is to create the facets, extract the facets. These cells are merged by KD trees by depending on some parameters. These parameters give us the limitation of the subcells. After this process, we find our deep and deep direction values. The main purpose is to compare our result with the geophysical assessment. For this reason, we choose 5 different values from each family, from software and in-situ result. The first one is our software result, and the second one is in-situ result. We can see that our result must be coherent because the location of the poles are close to each other. And the second one is the global comparison. With that way, we combine all of our data in situ results and the software results. And based on the observation, we can say that the accuracy of the poles mostly combine. After that, my friends will come and continue to geophysics.
I will finish the final part of field trip. We can see that in field trip we use the GPR method, and there is a machine with the IDS georadar as shown in the picture. And there on the left side we see the 4 red lines is our trace while we redo the field trip, and this part is the 3 families shown here. And then we go the very important step is the velocity test. We use the mental share to cover it, uncover it, cover it, uncover it. Because if you, in that case, we will get a reflection with the opposite polarity, and we can have the 2 different time, and we also have the distance. In that case, we estimate the distance over the time. We can get the velocity finally. And using software, we do some data processing like time calibration, bandpass filter, again, background removal, and envelope. The main, I think, very important part is about the GAN. It's used to amplify the diffraction and to make the signal visible at the same amplitude with the background signal. And these 5 steps is easy, so I don't say more about that. And then we analyze about the results. We can see that the profile 0 is corresponding to the family 1. Here we can see has a very strong signal in depth 50 centimeters. Also we can see here, and we can confirm that this signal shows a mantle pyro here. During this red light, maybe not so visible, we can make assumption that this is a moderate joint persistence, as the discontinuities were quite far from each other. And about the joint family 3, we have 2 pictures about profile 2 and profile 03. During profile 02, there has a signal, not so strong but visible in the depth of 15 centimeters. We are guessing that it may be a mantle instead, or the inner, or it will have an inner fracture. And the same we assume that it's a moderate joint resistance since the discontinuities are short and also far away from each other like that. And the final one is the family 2. We can see on the profile 4. In this profile, signal is more horizontal and all in a low value. We guess that because these parts are located in a less exposed place. So it has a low joint resistance since no evident discontinuity inside the rock. And the later we do step is that we calculate the joint persistence factor P is used to estimate our joint family. The formula is the formula is here, and we can know the percentage of the joint persistence and also average joint spacing. In that case, we can think that there has a possible that has a long crack lie inside the structure, but it's only the possibility, not the real one. So we just give a conclusion that this family 1 and family 3 are moderate joint persistence. This is finished about geophysical part, and our field trip is a combination about all the techniques from geophysical, geology, and also photogrammetry. That's all.